Hello, everyone. This is the first video you're going to get on astronomy. In general, what I tend to do is go through and talk about slides, talk about documents and such. And I'm going to use this jigsaw a fair bit. Here's, if you'd like to know what I look like, if you've never seen me before. I'm just going to, go through these slides and if we want to, we can go through and talk about various documents and whatnot. I've sent you out a number of different things, so we can talk about an article if we want. And you can see that here. Right. So you get the gist of it. This is kind of reviewing the material, and of course, you're seeing this on your own. If you have questions, you can come to the office hours. I've posted those. It's going to be, at the moment, it's going to be Tuesday and Thursday, 9 to 12. And I can do that at other times, but we need to talk about when that would be a good time, when it would be beneficial to you. Because it seems like, in my experience, most of you are going to do your work in the evenings or in the afternoons, and that might be a more beneficial time for you. What's the problem is I don't have internet at home, not to any great degree. I can do email, but I can't do Jigsaw. So, a time when you would be available would naturally be your class time, and that's what I picked. So another time it might be available, we can talk about. Anyway, that's all stuff that we're going to do at another time. We're not going to stress it here because we need to do astronomy. You need to see some information that we're going to talk about. Now, there's a couple of assignments in this presentation. There's a couple of videos I wanted you to watch, and I'm not going to go through those. This is just a brief sort of introductory thing. You should be going and watching those. I'll point them out when they come up. I'll talk about them a little bit. But the gist is to give you a sense of perspective. When we talk about distances in the universe, well, the universe looks like this picture. This picture is the Hubble Deep Field. And what happened, we obviously built the Hubble telescope and put it in space, and it ran for a while and looked at lots of different things. And it's really good at taking an image of one specific object. But what we did here is we pointed the telescope at one small part of the sky. I believe for this image, it's in the Big Dipper or in the Little Dipper. I can't remember, but it's so, if you look north tonight, and you should probably be going out at times and looking north when it's not storming, and looking at the sky when you can. But it just sat there and looked. And so this image is, if you've taken pictures where you've had to expose film for some reason, or you've taken a digital picture, but you have to hold it there for a long time, 2 or 3 seconds, because there's not enough light. What they did was they sat here for days at a time. I think something like 10 days, just exposing the camera inside the telescope. And this is picking up some of the farthest objects that we've ever seen. So when we want to talk about a sense of scale, there's a couple of different ways to talk about it. We can ask, well, how are, what kind of distances do we have between us and other things? And we can also talk about travel time. And travel time for us stinks. So we have to talk about something that can go reasonably fast, which is light. So first off, we've got a fairly cozy place in the universe. And it's a place that for a while we thought was fairly unique. It's got a lot of stuff in it. Right? We got stars and planets, and the planets have moons and different satellites. So other objects can have satellites. Just one thing orbiting another is a thing having a satellite. There are small objects, asteroids and comets, and things that are kind of in between. And the things that look like our solar system make up solar systems. Elsewhere in the universe, there's nebulas and collections of stars, which are galaxies. And eventually, that whole thing's in a group called the universe. It's called the universe because there's one of it. It includes everything. So it's, that's a little bit of a weird thing to define. Here are stars. In particular, this is a cluster of large blue stars. The things that we'll learn is that when we see large and blue stars, they tend to be young stars. That tends to be a very common thing throughout the universe. Is young stars can be large and blue. Old ones typically aren't. And we'll go into why that is. Here are two particular stars, Castor and Pollux, and you can tell that they're different. One is a blue star, and the other is not quite blue. It's got a reddish haze around it. That's probably yellowish. You can look at these in the night sky. They might be up now. In general, I'm going to know more about winter constellations, and this is kind of borderline. It's, at some places you can see it now, and some places you can't. We'll talk about that in chapter 2 as well. But if you want to know summer constellations, that's something you're going to have to research a bunch. I can kind of tell you some stuff about winter ones because that's when I teach. Here's a star. This one's particularly important. It's the sun. And so when we look at a star in detail, we can tell it's not just a pinpoint of light. It has features. We can see dark spots and swirls in it. We can see, I want to put the laser pointer right there. And if you can see right up above and left, you can see that there's a feature there. A little loop of material. And if you look at the right where the pointer is, there's another one. It's larger. And there's some features right there. And these things are fairly common. Now, of course, when we look at the sun, or we're going to look anywhere in the universe, we try not to limit ourselves to visible light. We're not setting up telescopes in the backyard. Astronomy takes in as much information as it can, and so we can look at different wavelengths of light. This is the sun in UV light, and there's a noticeable black dot right there. And that black dot is Venus. This was an image taken when Venus was in front of the sun, what's called a transit. And those events are particularly rare. The last two Venus transits were something like 2016 and 2012. They occur like a couple of years apart. And then they won't occur again for another 160 years. Mercury transits are a little bit more common. They're on cycles of like a couple of decades. And those are the only two that can go in front of the sun because they're closer to the sun. They can go between the sun and the earth. No other planets can. So here's some more views of the sun or of a star. You can see a lot more in this image of the features that leave the surface. And you can see some of those effects here. And this is colorized so that you get an idea of places where the stuff that's moving is energetic in this image. Upper left. I don't know my directions today. So, and then here's one that you might have been able to see. This is an image of a solar eclipse. So the moon is in front, and we're seeing the atmosphere of the sun around it. So if you got to see the eclipse, I think in 2017, it crossed America. The closest places to us that I can think of is Nashville and Charleston, South Carolina. You could have been along the path if you were around there. A lot of my students took the day off and went. I didn't tell them to, they just did. But, once in a lifetime, it's actually not once in a lifetime. Eclipses occur on a cycle. Eclipses in a particular location are more rare, right? So an eclipse that everyone can see in America is, even if they drive several hours, that's rare. Eclipses occur more often than you would think. They go on a cycle, and we'll talk about that cycle. I think that's chapter 2 as well. So there's planets, and we know of one planet. We're standing on it, but there's other ones. This is Jupiter, and we're looking at invisible light, and you can see the swirls of the atmosphere, and you can see a storm here and other storms that have popped up. All these eyes are essentially hurricanes, like we'd have on Earth, but they are swirls of high winds that are making rotation in the atmosphere. And of course, this one up here is very long lived. It's the Great Red Spot, and it's been around for about 400 years, I think, maybe 350. I'd have to look that up. And I know more about these when it's time to teach them. This is just an overview. Centuries of this thing swirling and being observed. Here's another planet. This one is Neptune, and it is a fairly far away big planet. You can see clouds in the atmosphere. You can see it has rings, and you can see a moon. This image was taken by Voyager 2 when it went by this moon of Neptune, which I believe is Triton. It has one big moon and several small moons. And Voyager 2 was a satellite that we basically flung off the Earth, and we hoped that it went through, we knew our physics, we pointed it in the right direction, and it went past all 4 of the big planets. And we took data on all 4 of them, but it just went past. It couldn't orbit. So now it's flying out through space. Here's another picture of the moon. We've sent a satellite behind the moon as it orbits the Earth. So the satellite orbits the Earth, and it just orbits from further away. And so this is capturing an image of the backside of the moon as it crosses in front of the Earth. Lots of planets have moons. Some planets don't. If you note, we'll talk about the pattern that we see. The small rocky planets have on average 1. All right, Mercury has, they go Mercury, Venus, Earth, Mars, Jupiter. The pattern goes 0, 0, 1, 2, 80. Big planets have lots of moons. Small planets, no. And the Earth is weird because we have a very big moon, and lots of moons are small. So here's some particularly different and big moons. This one is called Ganymede, which is one of the Galilean moons. We'll talk about their discovery. Essentially, Galileo looked at the moon in the telescope and saw that it orbited Jupiter. Here's Io, another one. This image is taken by Voyager 2, and we'll study these in detail because of their features, right? Ganymede is interesting because it looks like it has features in its ice. Io is interesting because it has volcanoes which blow material out into space. And then there are asteroids. We like to study asteroids because asteroids will end up being the remnants of the formation of the solar system. So they tell us something about how the solar system forms. And here we have Ida, which is basically a lumpy potato, being orbited by a very tiny satellite, Dactyl. And satellite asteroids are reasonably common. There's maybe about a million, estimated a million asteroids. A certain number of those we can see, a certain number we can't. And they occur in places we'll study, and we'll talk about, what asteroids do. But they're basically rocky potatoes. So there are also comets. Generally, when you see comets in the night sky, what you see is the glowing object with a tail coming off of it. And so, I've labeled these as to what they are, and we've looked at them in detail, looked at various ones in detail. If you were paying attention this summer, there was a comet in the northern sky. It was called Comet Neowise, and it was named after a spacecraft that was used to find comets and study them. And so it's sitting in the northern sky, and probably now you would need binoculars or a telescope to see it, and you would need to point it at the right spot. So that's the sort of thing you would need to do research on to see. The problem that we had is basically when it was visible, it thunderstormed every night. There were clouds in the northern sky every night. And the nights where the northern sky was clear, the ground was covered in fog. I mean, it was ridiculous. So seeing a nice image like this is kind of hard to do. However, these are not completely rare. You can often, there'll be reports of them every so often. And, the way I find out is listening to the 6 o'clock news. They'll tell it in the weather. They have an astronomical forecast. They'll say such and such objects in the sky. You can look here. I sent y'all an email about the Perseid meteor shower. Again, there were a particular set of days that I sent you an email. You should probably be able to go out tonight if you go look, or the next night. So this is Wednesday. So you can go out Wednesday night, Thursday night, Friday night, and probably see some meteors in the sky. And you're going to look in about the same place. You're going to look in the northern sky. You're going to look for a particular arrangement of stars. And, just basically wait. And the meteors will show up. And you can just go out any night and see them. Right? So you don't have to wait for a shower, but showers are when you will see them at a high rate. All right. So anyway, we're talking about comets, and there was one visible. When you look in the night sky, this is what you see. You see shiny thing with a tail, or maybe two tails. These tails will always point away from the sun because the sun is basically boiling off bits of the comet and leaving it behind. And it's going to basically be pushed away by the light. So you'll always see these tails like this, assuming you can see the comet at all. But what you actually have is basically an icy potato. Most small objects in the universe are potatoes. Most big objects in the universe are round balls or small flat disks or big flat disks. So this is an icy potato that's evaporating, and that's why there's an atmosphere around it. All right, so that's the solar system. The solar system is all the stuff that orbits a star. In this case, our solar system is everything that orbits the sun and the sun itself. And there's, I'll ask this question later, how many planets are there? There's been some debate as to how many planets there are, and at the time I've made these slides, there were 8. These first 8, and then Pluto and Eris are dwarf planets, which will define what we mean by dwarf planets. But we said these are things are kind of not rare enough to be planets in a sense, but we've defined that differently. So elsewhere in the night sky, elsewhere in the universe, you can see various, various accumulations of colorful light and gas. And some of those look like this, and they are nebulas. They're accumulations of gas that are glowing for some reason or reflecting light for some reason. Here's another one. I tend to point out often several of the same. These are probably the Orion Nebula or the Horsehead Nebula, some part of it, or the Eagle Nebula. Those were famous ones that were easy to image by Hubble and gave spectacular things. And you can see interesting stuff going on. All right, if you look carefully in here, there are lots of these little red stars here, and few of the bright white blue stars there. And those are our vision of those are going to be for various reasons. Right? We can probably explain these as lots of newborn stars, which aren't very bright, aren't very big, and will tend to be red until they grow to their final size, which may still be small or it may be big. But nebulas tend to be accumulations of gas where stars and solar systems can form. So galaxies. If you look in the place I'm telling you to look for the meteors and the comet, and you point your telescope in the right spot, you can see something that looks like this. I believe this is the Andromeda Galaxy. There's lots of them in the sky, obviously, but this one, you can look roughly in the northern sky, and you point at the right spot, and you won't be able to see anything with your eyes generally, but with a telescope, you can make out a disk of some sort. Most things in the universe are small, flat disks, at least from our point of view. And this disk is made out of billions of stars. And we're in a galaxy, which we can't get a picture of because we're in it. But we're in the Milky Way galaxy, which is also an accumulation of stars that look roughly like this, with about a billion, or somewhere between 1 and 100 billion stars. You'll know that there's smaller objects here which aren't distinguishable as stars. Most of these stars that look like they're in the background are really in front of this image. They're in front of the galaxy. But these two blobs are galaxies of their own that happen. They're smaller. They're called dwarf galaxies, and they orbit the big galaxy. And so here's two galaxies that are currently colliding. I say that because nothing actually hits each other. They just intermingle, and the things that are normally orbiting in circles are going to be distorted and pulled around. All right, gravity is going to mess this thing up, and this will make something unique out of it. But you can see that there's basically spirals. Right? It looks like kind of like a hurricane here and like a whirlpool here, and they're going to merge together and form some object, which might have spirals, it might not. Mergings of galaxies like this take millions and billions of years, and they tend to occur a lot in the early universe, basically because we'll find out later in this chapter, the galaxies are closer together then, so they're easier to collide. We're going to find out something unique about the universe that you probably already knew, but we're going to talk about it in some detail. So this is one of those videos. And I think if I get out of here and open one of these links, let me see if I can figure this out. I'm trying to figure stuff out. These things are weird. Here's the scale of the universe. Now I need to share my screen. I'm sharing my screen. I don't know what I'm doing sometimes. We're trying to figure this out. And what you're seeing is how I tend to lecture is sometimes I go on tangents or sometimes the first attack at something doesn't work. So we're going to try to look at the scale of the universe. So you can go through this and it plays some nice music. But the video is going to give you an idea of the universe. All right, what we're going to do is zoom out. We're looking at things that are about a meter in size. There's people, there's basketballs, there's teapots. And if you go look at this app, you can see the, there's a link in the notes. You can click on these things and it has little notes about them. All right. So what we're going to do is zoom outwards. And so it kind of gives you a sense of scale. Things that are on Earth look like this. And now we're starting to look at things that are not on Earth. Small objects, asteroids, comets, tiny satellites. Oops, there's Rhode Island. There's different objects we can see. Now we're talking about countries and states. When we go out, now we're talking about the dwarf planets and the big moons. Oh, there's Earth and California right next to it. And America, that's kind of weird. And Asia. And there's Venus. And now we're looking at the smallest stars. And we go further out. Small stars, bigger planets. It's kind of unusual. We'll talk about what these stars are. Oh, look, there's Minecraft. Yeah, it's fairly big. I didn't know that. Small stars, big planets. Now we're getting into everything's a star. This is not, these things are not in these positions. As we zoom out, the things you're seeing are larger and larger objects. We keep zooming out. And there for scale, that's the size of the solar system. At least from the Neptune to the sun, and then the extra stuff outside of it keeps going, and we just keep going out. There is, nice distance between stars. There's a light year. How long light takes to move in a year? How long light takes to move in about 3.25 years is a parsec. Distance to our nearest star is about 4 light years. And we just keep going. And we don't do that. We just keep going. We're starting to talk about star clusters now. And then we're starting to talk about galaxies, more galaxies. And, again, you can click on these and get some information about them as you explore this on your own. Now we're talking about groups of galaxies as we scroll out. And you can see there's a little counter here that is telling you roughly how many zeros are in the distance away from us. So we're going to try to talk about these things as we go on. All right. This is how far away the objects in the Hubble Deep Field are from Earth. It's about 10 to the 26 meters. So the observable universe is not that much bigger. About 10 times as big as we can see to the Hubble Deep Field. And the observable universe is just the stuff we can see. The trick with the universe is the only things we can see are things where the light has had time to get to us. So things further away could exist, but we won't know and they can't mess with us. We can't see light from it. It can't explode and show us that light until enough time has went by. All right, so we're going to zoom in the other way. Go wee. And then when we zoom in the other way, now we go smaller and smaller. This is the stuff you've seen in your classes if you took biology or chemistry. We zoom in, small animals, small insects, small crystals, small cells. And we keep zooming in. We're talking about the wavelengths of light because those are reasonable things to talk about here. Now we're on the scale of chromosomes and wavelengths of light. And we keep going in. Now we're looking at viruses and the constructions in our computer. And then we look at DNA and various things I don't understand because I don't remember biology. I do remember some chemistry a bit. We get into molecules by themselves and atoms, and we keep going. We keep going and going. And now we have the nuclei of atoms. Most of the atoms are empty space. We have an idea of what an electron is normally, but we kind of think it's even smaller than this. It's just a point. But we keep going. We're inside the individual particles, and we're not certain of anything beyond this, but we think these atomic particles are made up of other particles. And we keep going from there. And we talk about the sizes of particles that are really hard to find. And we'll talk about a lot more about neutrinos later. We keep going. And keep going. And a lot of this stuff I have no idea what we're talking about yet. We just keep going. Keep going. And we keep going. And eventually we hit a limit here. And the idea is that the big limit is the observable universe. The small limit here is based on theoretical physics. We're saying, what's the smallest a thing could be? And so there's some theories as to what kind of things might live at this range. And that's where we are at 35 decimal places to the small direction. Yeah. And then we go back out. There we are. So I want to stop screen sharing, and I'm going to turn that music off because as much as I like it to begin with, I don't like it now. And then we're going to go back to the presentation. So I'll tell you, I want you to go see this main video. It's worthwhile. It was obviously made in the 70s. I think it's pretty groovy, but it's does the same sort of thing. All right, so the universe is big, and the range of scales that we're going to talk about is kind of big. All right, we're talking about a range of about 60 zeros. So the stuff that is astronomical is going to be that about 25 zeros out. Those are some big distances. And if we wanted to travel those distances, we kind of have a problem, right? The best way we have to travel is basically to build a rocket and shoot ourselves off somewhere. And when we tried that, we went to the moon, and it took several days. It took 3 or 4 days to get there. And that's using rockets to push ourselves there as fast as we could. So light travels a bit faster, and we can talk about distances in terms of the time light takes to travel. And so when we talk about going to the moon is about 2 light seconds away. And you can notice that if you listened to the Apollo recordings where they landed people on the moon and then talked to them, there was always a delay of about 4 seconds. 2 for our signal to get there, 2 for their signal to get back. For lots of other distances, I ask you in the homework, how long does it take for light to get from the sun to Mars? That's going to be on the ballpark of 20 minutes. I think in your homework, it's going to be less than that because you're using an average distance. Light from the sun to the Earth takes about 8 minutes. To get to the nearest star is going to be 4 years. And a light year is a huge distance, which we can calculate. We use the speed of light and the length of a year, and we end up with about 3, 6, 9, 12, about 1,000 million billion, about 10 trillion kilometers, or 10 to the 16 meters. Now, of course, there's a video here. I'm not going to go through this video, but what it does is it starts at the sun and it travels 1 light second per second. And it takes 8 minutes to see the Earth. It takes about 30 minutes to get to Jupiter, 45 minutes to get to Saturn. And that's the whole video. It's 45 minutes of you traveling through space. It does get shrunk up, I think, in the link that I show you, so you can, see it in a reasonable time. But you can find the original video and watch it for 45 minutes if you want. I'm not going to do that here. I think it's just cool. So that's kind of, when I show this in class, you see the size of the universe and the emptiness of it. And I have to ask you kind of, how are you doing? We're used to a world that's not that big and not that empty. And that's what the universe is. It's a big, empty, and old place. So this is kind of the theme for the rest of this video. The universe is big, the universe is empty, and the universe is old. We move really fast through it, we think, and everything seems to be moving further away from us. So the universe is big and empty, right? If we talk about the light going to the moon, it's a second or two. To the sun, it's 8 minutes. To Sirius, which is a bright winter star, it's 8 years. And to the nearest big galaxy is 2.5 million years. Everything we see, the light from it is old. And so when we look at this light coming from an object, we're seeing back in time as well as far away. So the nearest stars, if you look in the southern sky, I don't think you can see these here. You might be able to see like the top couple of stars here, but you can't see these stars. They're basically for lower latitude, for southern latitudes. This is the constellation Centaurus, which is supposed to be a centaur. You can kind of make it out. There's the horse's body, and then there's the man's body. Arms spread out. And so there's a lot of stars here and a lot of young forming stars. And one of these is the brightest star, which is why it's called alpha. The second brightest is beta. The third brightest is gamma. And right around alpha is very, very close, is a star that's just a little bit closer to us, which is called Proxima because it's the closest. And that light is 4 and a bit years old, 4.4 years old, because that's as far away as the nearest star. That's a huge distance. If we talk about things that we're traveling to, people just can't go there. The satellites we've sent out, Voyager 1, Voyager 2, the Mariner and Pioneer missions, I think that escaped. I'm trying to remember which ones. New Horizons, which we sent to Pluto. All these missions that we send out will get there if they're pointed that way, which they're not, in millions of years. Light is very fast and everything is very, very far away. So we look at Orion, which is a constellation, basically rises due east and sets due west, roughly. I think I pointed out this star rises due east and due west. And this whole set of stuff has lots of nebula in it. And particularly the Orion Nebula is here. I think the Eagle Nebula is somewhere up in here. We can map it out, and you can tell this is vaguely like a person. There's shoulders, a belt, and knees. This is a hunter, so there's a shield here, and a sword goes up over the top of the body here. And we'll look at that when we do star tours with the planetarium software. Most of these stars are 1,500 years old when the light gets to us. We're seeing 1,500 light years away. And it's kind of interesting, right? Is that there was a whole big thing last year in the news of this star here, which I swear to you is pronounced Betelgeuse, like the movie and the person in the movie. This is pronounced Betelgeuse. This star was changing brightness and changing shape in such a way that led us to think it was going to blow up in a supernova. And then it didn't. If it had, it would have done that 1,500 years ago. And we would have just noticed it now. That would have been when the light gets to us. Here's some of the internals of, this is canted on its side. So this is the belt. This is the scabbard for the sword. This is the shield here. And this is going to be where the sword comes up. And then you see shoulders and knees here. And again, all this light, all the light from the nebulas, all the beautiful stuff around here is about 1,500 years old. Now, of course, all these things have been sitting there for millions of years, just doing its stuff. But the information is 1,500 years old. So all these things I'm telling you about going out and looking at the night sky this week, you're looking at about this area. You can probably see this W shape in the sky if you look north. And then you'll see some of these other stars here. Right? This is two constellations, Andromeda and Pegasus. This is supposed to be a winged horse. Can you see that? I can't see that. And Andromeda is supposed to be a woman laying down. I see like 3 stars in a line. Whoever was looking at the night sky when they named these was very imaginative. But there's a little fuzzy dot, which is the Andromeda galaxy here. And that light is 2.5 million years old. So that kind of gives you a sense of the scale of the universe. Is nearest stars are so far away that light takes hundreds of years to travel. Galaxies are thousands of times farther away. And groups and clusters of galaxies are going to be thousands of times further away there. Eventually, the observable universe is this massive thing that we're very alone in. This is the link with the Sun to Saturn in 45 minutes. And this other link is when we show you pictures of the solar system, we can get the sizes of the objects correct, or we can get the spacing between them correct. It's very hard to get both correct. And this video is about people going out in the desert to get the scale correct on both size and distance. And it gives you an idea. Essentially, you need to put all the planets in an area such that the sun is a beach ball and the earth is a marble. You need about 7 miles of space. So these scales, these numbers with lots of zeros, lead us to try to come up with scale models. And so one scale model that gets repeated a lot is the spacing between planets. Excuse me. If you hear my phone go, uh-oh, if you hear the phone go, uh-oh, that is people telling me what y'all are doing or what the rest of the teachers are doing. Basically, what do I need to be doing? That's why it says, uh-oh, because I want to know what now. So a lot of places have layouts of scale models. So if you go to Washington, you can go to the Air and Space Museum. And right in front of it, they'll have several planets marked out for the spacings. There's another one. If you've ever been to a snowshoe resort, you go over the mountain into the valley where you can't get a phone signal. Down there is the Green Bank Observatory, which has a massive radio telescope. And because they're listening at radio waves, they don't have any electronics that transmit there. So it's kind of interesting. So they have one there, and it's several miles long, and you can bike along and see the little exhibits. And in front of the main building is like the first 4 planets. So city blocks could hold a scale model of the solar system where the sun is a grapefruit and the earth is the ballpoint in a ballpoint pen. The nearest stars would cross the country, and the Milky Way galaxy would fit in the Earth's orbit. Even with scale models, the sizes are kind of ridiculous. That gives you an image. This is the nearest star is in San Francisco if the sun is in Washington. And the Milky Way fits between the sun and the earth on that scale. So even with scale models, big things are massively big. The Milky Way is a lot of galaxies and is one of a lot of galaxies. And there are a lot of stars in a galaxy. And we can make an estimate. This is, if you're in physics, you would be doing this order of magnitude estimation at some point. It's an optional thing you can do. Optional assignment. But you can guess, there's about 10 to the 22 stars. If you could associate a single grain of sand with each star, you could use all the beaches on Earth to do that. And there would be just enough sand. There are a lot of stars. 10 to the 22 is a lot. It's basically an uncountable number. You're not going to sit there and count that high. So another scale model that we tend to use has to do with time. We take the history of the universe and we compress it to 1 year. And what we find is that for a large portion of the universe's existence, nothing happened. But we'll go through this scale model. Right? The very beginning, it's going to be New Year's Day. Everyone partied too much the night before, and it's you start off with the Big Bang, and then sometime in February, galaxies start to form. Right? The events here are basically stuff forming out of energy. And so you'll eventually get atoms forming, and then the atoms form molecules, and then you eventually get clouds of gas, and eventually you get galaxies, as basically there's a big push outwards, and then gravity starts pulling everything back together. And that's going to be the story for the entire year. Gravity pulling against some other force, and gravity usually wins. So in February, gravity wins and makes galaxies. And then nothing happens. So galaxies are going to keep evolving. Stars will form, they'll die, they'll reform. The material that made up old stars will make new stars. This goes on about in September. So for scale, the Big Bang would have been 14 billion years ago. The Earth forms about 4 billion years ago. A bunch of rocks are going to collide together and accumulate into a round object that is the Earth. And it's going to happen to all the other planets. The solar system forms. And a little bit later, the particular elements on the Earth are going to self-replicate. You're starting to get early life to form. And at the very end of the year, we'll try to talk about what kinds of processes might have sparked that life, and could it have happened anywhere else? So the early Earth happens, and then not much else for a while. So in December, we're talking fairly close to, um, you know, mid-December, we start an explosion of development of new forms of life. If you remember your high school biology, you'll remember about this. Christmas Day, you get some dinosaurs. Isn't that great? They break by the 30th. And then all of recorded human history is going to occur New Year's Eve. And people, the first forms of people, show up at 9 o'clock. They're the ones that come to the party early or on time. The fashionably late people, modern humans, show up 2 minutes to midnight. And then it scales up from there. All of history is going to be in the last 30 seconds. Agriculture's 25 seconds out. 10 or 11 seconds out, you get the pyramids. A second ago will be chapter 3 in our book, Kepler and Galileo talking about Earth scientifically and talking about its actual position in the universe. Your lifespan will be about 50 milliseconds, I think. It should be on the next slide. Yeah. This is kind of, if we modeled the history of the universe into 1 year, we don't really have very much of it, do we? At best, we have, if we're generous, we can call it 10 seconds. For your life, it's less than a second. The Earth is also moving very, very fast. There's a lot of stuff we don't perceive. We don't perceive the bigness of the universe, and we don't perceive the age of the universe. Our local area, right? How far can you travel in a day? 500 miles, maybe, if you're careful, unless you get on a plane. In theory, you can travel the whole of the Earth in a day, but realistically, 500 miles. Your lifespan is 70 years. These are all tiny numbers compared to the universe. And the fastest you can go, if you walk, it's a few miles an hour. If you drive, the fastest car in the world is 250 miles an hour, 275. Um, drag cars are going to be like 350. But, sending someone to the moon is going to be only a few thousand. We're starting to talk about rotational speeds now. The Earth moves at a very fast speed because it's rotating. It's also a big object. It takes it a day to rotate. But if you take the size of the Earth and the time it takes to rotate, you can work out at the equator 1,700 kilometers an hour, about 1,000 miles an hour. Now at the pole, you're just kind of rotating in place. You're not actually moving relative to the Earth, relative to the center of the Earth, let's say. The Earth, however, is going around the sun, and if we take the Earth's orbit in a year, we figure out it's 107,000 kilometers an hour to go around the Earth, at the speed the Earth orbits. But now the sun is not stationary; it's moving. The sun orbits in the galaxy. It's about 27,000 light years from the center, and at the speed it is moving, it'll take 230 million years to orbit, which gives us an idea it's about 800,000 kilometers an hour, which is about 8 times what the Earth is doing. There's no real way of saying anything's at rest we end up with, because this galaxy is moving relative to everything else. And eventually we realize the universe is expanding. We're never actually sitting still. How do we know the universe is expanding? Well, we look at other galaxies. They're all moving away from us. The first person to do that is Edwin Hubble in the 1920s. Sat and just cataloged out. There was a debate about what galaxies were. People thought they were nebulas, and other people thought they contained stars. And what Hubble did was look at the stars in particular nebula and realize that they had to be massively far away for what they were. And so he realized they were galaxies. Then he started cataloging galaxies. And when he did, he realized that aside from the ones local to us, they're all moving away. And the further away they are, the faster they're moving, which implies that they're moving away from each other. Now, our way of modeling that is kind of weird. We talk about raisins in a cake. All right, if you have a ball of dough and you throw some raisins and knead it in, they're all basically in a small thing, a small little ball of dough. And then you bake it, and the cake rises. It spreads out. And the individual raisins inside are all getting further apart from each other. And so from the perspective of one of them, right, if we have some of them and you can say they're a centimeter apart, from the perspective of one of them, the nearest one might get 3 centimeters apart, but the furthest one will be 9. And so it's 3 times faster because it's 3 times further away. This is, just a property of the dough expanding. And so we see the same behavior in the universe. It implies that the universe must be expanding. That is a lot of information about the universe. A huge amount of information about the universe. And so I kind of just want to talk to you about some other stuff. We've seen, so here I am now. Here's my pretty face, and I'm looking through your notes. I talk about the Hubble Deep Field. I sent you a article about that. And it's the details, you look at it for 10 days, and we're seeing 10 billion year old light. And I've talked a little bit about our understanding of the universe. I give you some more detail. We're going to go into it later when we talk about the beginnings of the universe. When we talk about the Big Bang, that comes at the end of the year. But we talk about, I give you this article talking about our understanding and how our understanding evolved and how Hubble figured out that the universe was expanding. So you can look through that. It's fairly, it's fairly straightforward, I think. There's some interesting stuff. And so, yeah, that's about it. So you have a homework for this week. I kind of gave you some things that you want to look at in your textbook. Basically, do you know your textbook? Have you done the reading for the class? A lot of the in-person classes are kind of, we talk about stuff that's occurred, and now I can't talk with you about it, so that's a good thing to come to the office hours and ask questions. But we talk about things that's in the reading and in the textbook, and I really want you to go. A lot of people had questions about the appendix. All right, question 5, the contents of pages A1 through A31. Your textbook. Some of you got new textbooks. Some of you didn't. You got whatever's laying around here. There's a page that says appendices. That is where you'll find A1 through A31. They're actually labeled at the bottom. And what I'm getting at is, what is this information? It's beneficial stuff. Star charts are here. So when you do observations, you can take these out. These charts don't change over your lifetime, so they're fairly steady. And there's several of them, so you can pick the one for the right time of season. And then some of these you'll use, trying to find, like, you will come back to Appendix E, which is the planetary data. You'll see that a fair bit. So when I write homework solutions, I'm going by the textbook solution if I use a textbook problem. You're perfectly welcome to Google for those numbers, but it's just more convenient to have them there if you have the book open. And there's other stuff in there. And what will happen is, if you Google a number, you also have to Google, in the right context. Is, how big is my unit? Is it millions of kilometers? Or at least one person, I looked at their work and they hadn't put the units in. And so the numbers in here was like 230, but it's 230 with 6 zeros after it, which changes your answer significantly. So, there's a lot of stuff. I wanted you to familiarize yourself with the textbook, but I also want you to, think about the universe in this chapter. And in the next chapter, it'll be the night sky. And in the third chapter, it'll be the history of astronomy. So I wanted you to think about that. But I also wanted you to go outside, and I want you to do some background research. I asked you to go look at a particular website, the Astronomy Picture of the Day, mostly because they're pretty pictures. And that's where I get a lot of the pictures for these slides. And they're interesting. They tell you, this is the thing about astronomy, is the field is constantly evolving. And basically, when you're learning stuff, I'm learning stuff. All right, it's in 5 years, I've not had a class that has not improved, where I've just learned new material and then I tell you about it, hopefully excitedly when I tell you about it. But I just, the last few questions are familiarizing yourself with the outside world and then finding out about you a bit. Tell me what you think about things. What do you want to know about astronomy? If there's something interesting you want to know, I can try to make sure to hit that. And if I don't, you can ask me about it. That's kind of an important thing to do. So that's kind of it. That's the video. That's chapter 1. Now, if you need to know how to do calculations, I'll try to have videos like that. If you need a particular topic discussed, I'll try to have separate videos on that. Basically, those separate things are for particular things, and then the slides and the readings are basically a general overview of things. So, yeah, that's about it. That's the video for this week. Next week we'll go over the night sky, and I will show you planetarium software that we use, or at least I use it. Um, I recommend y'all use some if you can find it and download it and use it on your home computers. Um, don't pay for it. There's good free stuff out there. Don't pay for it until you decide you think you need it. Anyway, yeah, that's the video. I hope y'all are having a good day. It's late. I want to go home.